Let's talk about a couple more types of infinite series. Maybe not types of infinite series, but ways that we can decide if a series is convergent or not. Um, in this section, and this is actually two sections, but in this video, we're not necessarily concerned with what the value of what the series converges to, so much as is it convergent or not. So sometimes it's kind of it is difficult to figure out if what the infinite sum is, but it's useful still to figure out if it's convergent or not. So the first test that we are looking at is called the integral test. So if we have a function, and all three of these words are important for this test. So continuous, positive, decreasing function on this interval 1 to infinity, and this could really be anything, as long as it's defined. This it doesn't have to start at 1; it can start at any positive number, really. And we have the infinite series, or we let a sub n equal f of n. So if f of x is 1 over x, then the series is 1 over n. Then this infinite series is convergent if and only if the improper integral for f of x is also convergent. So in other words, we have the improper integral from 1 to infinity. If that converges, then this infinite series converges. If the improper integral diverges, then the infinite series is also divergent. So let's look at an example to see how this works. So we have the infinite series 1 over n squared plus 1. This is so continuous. We don't have any discontinuities. That denominator will never be 0. Positive, so 1 over 2, the sum of two positive numbers will always be positive. And decreasing, so the only variable we have here is the n squared, and that's only going to increase. As n increases, I should say. As n increases, this fraction gets smaller and smaller. So it is continuous, positive, decreasing. So we can use the integral test. So we are going to integrate from 1 to infinity, 1 over x squared. You can leave it as n if you like, but we'll write 1 over x squared dx. And so, of course, this is the limit as t goes to infinity, the integral from 1 to t, 1 over x squared plus 1 dx. So the integral of 1 over x squared plus 1 is arctangent. So we have arctangent, and we'll go ahead and plug in the values here. So arctangent of t minus arctangent of 1, which is pi over 4. So as we take this to infinity, we get pi over 2 minus pi over 4, which is pi over 4. So that converges, which tells us that this infinite sum converges. Okay, so and these will be very simple integrals to complete. No big trig substitution or anything like that. They'll be pretty simple. So next, let's look at a p-series. So the series 1 over n to the p is called the p-series. P can be any number, any real number. And so if p is greater than 1, then this series is convergent. If it's less than or equal to 1, then it diverges. So example 2a, we have 1 over n cubed. So in this case, p is 3. That is greater than 1. And so this series will converge. And that's all you need to know. N equals n to the 1/3. So p is 1/3. That is less than 1. And so this one will diverge. Now, remember from what we said in maybe the last video, it was the last video, this limit, just to remember, this limit does go to 0. So the terms do go to 0, but the series still diverges. So keep that in mind. Again, just because the terms go to 0 does not mean that the series converges. If it does converge, then they will go to 0, but the reverse is not necessarily true. All right, so let's look at this series. So determine whether this series converges or diverges. So can we do the integral test with this? Is this continuous from 1 to infinity? all of these, it would always be defined. So this only discontinuity would be, I guess, at zero, but zero is not even in the domain. So, and the domain is only positive numbers. So certainly from 1 to infinity, it is continuous. At 1, it would be 0. After 1, it will always be positive. And is it decreasing? So let's take the derivative and see if it's decreasing. So if we have ln of x over x, let's take the derivative and we'll see if this is decreasing. So use the quotient rules. So we have the bottom times the derivative of the top minus the top times the derivative of the bottom, which is 1 over x squared. So this is 1 minus ln of x over x squared. So we need to, where is the derivative positive? That will tell us where the function is increasing. So that's always positive. So 1 minus ln of x needs to be greater than 0. So 1 needs to be greater than ln of x, and so x needs to be greater than e. Sorry, we're looking at decreasing. So this needs to be less than 0. That was my mistake. Decreasing less than 0. So x is greater than e means that this function will be decreasing. So let's integrate from 1 to infinity. ln of x over x dx. We can use substitution, so u equals ln of x, du equals 1 over x dx. So this works out. We get infinity. If we plug in 1, we get 0. And we get just u du. So we get 1/2 u squared. And so this is going to go to infinity. We can work out the limit if we like, but this is going to go to infinity, which tells us that this series diverges. So the integral diverges, so the series diverges. Okay. Now, if we had found that this was an increasing function going to infinity, then the integral test would not work, and so we couldn't use it at that point. So on your homework, I'm sure if it tells you to do the integral test, it probably will work. But something you should test if you get to the test, the actual test, and you have these series where you're not sure what test you can use. So we've seen the integral test. We're about to see the comparison test. If you're not sure which one you can use before you use the integral test, you do need to figure out if it's a decreasing function. So just keep that in mind. Now, the next one we're going to look at is called the comparison test. And so the comparison test is basically looking at if we have two series, and let's say that one series we know it converges or it diverges. So if we have a series A and a series B, if B converges and A is less than B for all n, then A also converges. And then the other way, if B diverges and A is greater than B for all n, then A is going to diverge. So if you have this series, and we'll kind of use, it's not continuous, but we'll use a function. So we have B looks like this. So here's B. And then A looks like this. So A is the lower one. Then if B converges to some finite number, obviously A is not going to be infinite. A is also going to have to converge to a finite number. And then likewise, if we have some series B that looks like that, and B diverges, and A is greater than B for all of these, then obviously A is also going to diverge. So that's the idea. That's what the picture kind of looks like. Now, in practice, it takes a little bit to get used to how do you figure out what series you can compare this to, because you can't just pick any series. I mean, it has to be somehow related. So in this case, we have 5 over 2n squared plus 4n plus 3. Typically, you're going to figure out either a p-series that we saw a minute ago or a geometric series. So if we have 5 over 2n squared plus 4n plus 3, we know that this is always going to be less than 5 over 2n squared, because this one has added terms in the denominator. So this denominator is always bigger than this denominator. So this fraction is always smaller than this fraction. So that's the idea. So if you're adding terms in a denominator, you can always remove those terms and you end up with a bigger fraction. And then we can just kind of pull out the 5 halves, and this is 5 halves times 1 over n squared. So we know that 1 over n squared converges. This is a p-series where p is greater than 1. So then if 1 over n squared converges, we know that 5 over 2n squared converges. So multiplying by a constant will not change whether a series converges or not. And if this one converges and this one is always smaller, then our series that we are interested also converges. So there's not really, I mean, I guess this is math, but there's not arithmetic, algebra, calculus, anything like that. We're really just looking at series where we're comparing terms. So all the terms in this are smaller than all the terms in this. And if you like, I didn't write out the terms, but you could figure out. So if we call this one a sub n and this one b sub n, you could write out a few terms just to be sure that the terms that these terms are always, the a is always smaller than b. So when n equals 1, we have 5 halves. When n equals 2, we have 5 eighths, and so on. I'm not going to figure out the terms, but when n is 1 in this one, we have 5 over 9, it looks like. So 5 over 9 is less than 5 halves. When n is 2, we have, that would be 8 plus 3, so that'd be 5 over 19. And 5 over 19 is less than 5 over 8, and so on. So you can figure out a few terms. You don't have to obviously do many, but just to kind of get an idea, to make sure as you're getting used to this that these terms in this series are smaller than the terms in this series. And if you know this one converges, then this one will also converge. All right, then the next one is the limit comparison test. So let's say we have two series with positive terms. If the limit of the ratio goes to or equals c, as n goes to infinity, where c is a finite number and c is positive, then either both series converge or both diverge. So the idea here is we want to find a series that converges. We don't know if this one does or not, but let's find a series that we do know converges. It's kind of similar to this one. It helps if it's similar. So we'll call this one A. Doesn't really matter which one you call which. And then what's a series that's similar to this so we know would converge? Let's say 1 over 2 to the n. We know that that one converges. So this one converges. So now we can do the limit test. So the limit as n goes to infinity. Let's do an over bn. So this would be the limit as n goes to infinity. 1 over 2 to the n minus 1 over 1 over 2 to the n. Let's simplify this fraction. We get limit as n goes to infinity. This would simplify to 2 to the n over 2 to the n minus 1. If you like, we can divide everything by 2 to the n. And we get 1 over 1 minus 1 over 2 to the n. This will go to 0. And we end up with the limit equal 1. And this is not equal to 0. It is positive, and it is finite. So that tells us that since B converges, so since Bn converges, and limit is positive and finite. AN also converges. Okay, so three tests. We have the integral test, we have the direct comparison test, and we have the limit comparison test. So be sure you're familiar with when you can use these because you can't use them all the time. And be comfortable using all three because you can't use all of them all the time, like I said. So you got to be familiar with when you can use which ones and how they work. So if you have any questions about any of these, you can please let me know.